In this lesson, I'll show you how to determine the pH of a solution containing an anion acting as a base. The question reads, find the pH of a 0.100 molar NaCHO2 solution. The salt completely dissociates into Na plus and CHO2 minus, and the Na plus ion has no acid or base properties. So the anion acting as a base is this one right here. The first thing that I want to do is write a chemical formula where this anion is reacting with water. So we have CHO2 minus, and it's in its aqueous phase, plus liquid water, and this yields, given that CHO2 minus is acting as a base, that means the H2O will be donating its proton to this molecule. And because of that, we form hydroxide, also aqueous, plus HCHO2. And if you're unfamiliar with this molecule, it's actually formic acid. Now to find the pH of the solution, we need the concentration of OH minus, because using the concentration of OH minus, we can then find the concentration of H3O plus and from there find the pH. So let's prepare an ice table, and we'll be ignoring H2O because it is in its liquid phase. The ice table, as usual, consists of 3 rows, I, C, and E. Because NaCHO2 completely dissociates, we can say that its concentration is the same concentration as CHO2 minus. So 0.100 is the initial concentration of CHO2 minus. We'll ignore that. The concentration of OH minus is going to be approximately equal to 0 because we're told that CHO2 minus is a weak base, and the concentration of formic acid is 0. So let's come up with an expression for the equilibrium of these 3 molecules. I'll start by setting any one of these as x. So I'll set this one as x, and I'll create stoichiometric ratios with the other molecules to find their change. Make sure that this equation is balanced, and I'm going to tell you ahead of time that it is. So this is a 1-to-1 ratio. That means that this will be x, but negative because it's comparing reactants with products, and similarly that's negative x. To find E, we add I and C together. So I'm going to add these two numbers together. I'm going to add 0 with negative x, that's negative x, and 0 with negative x. Now as I mentioned, we are looking for the concentration of OH minus. To find the concentration of OH minus, we will set up an equilibrium expression related to K sub B. Here's what I mean. K sub B is equal to the concentration of the products, OH minus, the concentration of HCHO2 over the concentration of CHO2 minus. Notice that we did not include the concentration of H2O because it is a liquid. To find the concentration of OH, I can now substitute each of these expressions into this equilibrium expression. And here's what I mean. Negative x times negative x, pretend that this is negative x and negative x, we end up with x squared over the expression for CHO2 minus was 0.100 plus x, and that is equal to Kb. Normally they give us the Kb, but in this case they don't. But we can use this relationship to find out what it is. In fact, Kw from previous lessons we learned is 1.0 times 10 to the power of negative 14. And since we have formed formic acid, we can use its Ka, its constant, as 1.8 times 10 to the power of negative 4. And that can actually be found in a table in your textbook. I actually happen to find it right here, and I will write that in. Using the relationship shown here, we can actually find Kb and then substitute that value into the equilibrium expression. The formula is Kw is equal to Ka times Kb. I'll substitute this value here and this value into here and solve for Kb. And here's how to do that. Open up your calculator, type in 1.0 times 10 raised to the power of negative 14, and divide both sides of the equation by 1.8 times 10 raised to the power of negative 4. This gives us a value for Kb that's 5.5 times 10 to the power of negative 11. And we'll reduce this down to two significant figures. It should be 5.6 times 10 to the power of negative 11 as Kb. As mentioned, I'll substitute that right into there. And just to make things clear, I will be working underneath here. So I'll rewrite this expression right underneath here. Very nice. Now we can finally solve for x. And once we solve for x, we can come up with the equilibrium concentration of OH-, which we can then use to find the pH of the solution. Now, because this number is so tiny, I can make the assumption that this plus x, we don't need it. And you can only make that assumption if your K value is really small, like it is here. By making this assumption, it actually makes the solving process for x squared, rather x, easier. Otherwise, if you don't make it, then you have to use the quadratic formula, which takes more time. So I'll solve for x by multiplying both sides by 0.100. This cancels out with that. And we're left with 0.100 times 5.6 times 10 to the power of negative 11 is equal to x squared. I'll multiply these two factors and then square root both sides of the equation. So that's what happens when you multiply these two. And we square root, giving us 2.366. And we need this to two significant figures. So I'll write down 2.4 times 10 raised to the power of negative 6. Since we square rooted both sides, I didn't show it, but here it is. You should end up with a plus minus version of this number. Plus minus 2.4 times 10 to the power of negative 6. We have to decide which of these two versions, the positive one or the negative one, works. Of course, we have to choose the negative one, even though it seems unorthodox. But we choose the negative one because when you substitute it into here, negative times a negative makes a positive, and we need the equilibrium expression to be positive, otherwise it doesn't make any sense. That being said, if I substitute that negative number into here, I should end up with 2.4 times 10 to the power of negative 6 molars. I finally have the concentration of OH-, and now I can work on finding the pH. So here's how to do that. You need to know this formula. Kw is equal to the concentration of H3 plus times the concentration of OH-. We already know what Kw is, and we discussed it earlier. 1.0 times 10 to the power of negative 14 is equal to x, which is what we're looking for, representing H3O plus, times this number, 2.4 times 10 to the power of negative 6. We'll solve for x by dividing both sides. So that's Kw on your screen, divided by 2.4 times 10 to the power of negative 6. This gives us a value to two significant figures of 4.2 times 10 to the power of negative 9 is equal to the hydronium concentration. Now, all we do is substitute this into the formula for pH, which is negative log of the concentration of H3O plus. So we'll plug that into there. Negative log, and we have two significant figures here. So following the decimal of the answer we get, it should also have two digits. We get 8.376. We should stop writing after the 7 and round up to 8.38 as the pH of the solution. And there you have it. That is how to determine the pH of a solution containing an anion acting as a base.